Okay. Good afternoon, Dr. Costaglos. My name is William Kelly. I am a first-year master's student here at Northwestern in the computer engineering pathway, AI machine learning specialization to be specific. Um, I didn't work with any group mates, but I didn't work with any group mates, but let me tell you about how I built a machine learning model for breast cancer detection. And if this is the TA's grading this, hello to you too. My mother beat breast cancer in 2021 and ever since has stressed the importance of early testing and early detection so that treatments are more effective. Furthermore, the accurate classification of benign tumors, those are tumors that don't spread, from malignant tumors, which are tumors that do spread, can prevent patients from taking unnecessary treatments. So for the end of the quarter project, I chose to explore how machine learning and data analysis can be used to classify whether a breast cancer tumor is benign or malignant. So to start, I found this data set. This data set is a public data set of solid breast masses or tumors, and it was published by Dr. William H. Wolberg, who is a physician at the University of Wisconsin Hospital in Madison, Wisconsin. He created this data set by taking fine needle aspirations, which are basically you take a needle into an active breast tumor or breast mass, and you get some fluid, and then basically there's a lot of measurements that go on. So they send that through a graphical computer program. And once that program is complete, it pretty much kicks back 10 features from each one of the cells in the sample, and then calculates the mean value, extreme value, and standard error of each feature in the image, and returns a real evaluated vector. So that leaves us with 30 features. As you can see here, it's not going to show all 30, but there's 32 columns. The extra two are diagnosis and ID, which are the two most leftmost columns. And yeah, so essentially, I chose to use a classification route to solve this problem because it's pretty much perfect. Basically, you can take basically in a classification problem, you can take features from two or more data sets and compare them against each other. That's perfect for what we want to do here, as I was looking at this diagnosis column for being the categorical data, but we'll get to that. So to prepare the data and make sure that, we were good to go and working with a good data set, I ran those couple commands. The data set is null sum, which basically checked to see that there's no holes or empty spaces. I did later on find the issue where there's extra space, which kind of threw off the way that it was compiling stuff, but I just took out all those extra spaces and it worked fine again. So here you can see everything else is a float and diagnosis is an object. So that's our categorical data. Floats numerical, categorical for strings. So then we moved on to basically encoding and splitting the data set. Like I said before, categorical data are variables that contain label values, so more strings than numerical values. Basically, we're going to use a diagnosis section, as you see here. But to do this, we need to change the M and the B to something that can be read by the algorithm. So a 0 and a 1. So basically, we change the 1 to malignant and 0 to benign here. So you can see that in that little demonstration on the table there. And I utilize the label encoder by Scikit. It was a Learn library in Python, which converts categorical data to numbers, and that was useful in this case. Here, you can find a lot of correlation between the mean features here, and that helps you understand the relationship in between them. So I use some Seaborn and Matplotlib libraries to produce some visualizations between the mean features. I also used pandas and a couple others, but these ended up being, the best representation of that. Next will be splitting the data and feature scaling. So obviously, to train any machine learning model, you have to split the data set into training and testing data. To do that, I use the train test split function from sklearn. So the Y variable here represents the target variable, which is a diagnosis, the benign or the malignant tumor. And then the X represents all the other features, so all the features to the right, and just includes all the features aside from ID and diagnosis. So the data set was split into 75% trained data and 25% test data for this case. In addition to splitting the data, I also needed to feature scale, which means bringing all the features to the same magnitude. And I was able to achieve that using the standard scalar feature on the X variable, which held all the extra features. Next is model selection. So I only tested 3 models: logistic regression, the decision tree classifier, and the random forest classifier. Basically, X-train, the model takes basically X-train features and then Y-train the labels, as I said before, and then it trains it each using those dot fit, the dot fit from the library that I was using, the decision tree classifier from sktree. So each of those takes dot fit, and then dot score computes the accuracy and everything and gives it back. And from this step, we went to the confusion matrix. And the indices stand for true positive, true negative, false positive, and false negative in the decision matrix. And that essentially describes the performance of the 3 classification algorithms that I chose. So to conclude, what we got was, out of the 3 models, the random forest classifier yielded the highest accuracy of 96%, which I would consider to be a success for my first classification problem on my own. I ran into a few problems with, I'm sorry, at the very bottom, that's just pretty much showing how the random tree classifier was working. Well, actually, that one is showing the second one, which was the decision tree, I think. Yeah, that one was showing the second one. But if I would have put model 3, it would have shown the third one. And anyway, I'm sorry. I did run into a few problems in the data CSV. Like I said, that there are those white spaces, which was easily handled. When I was doing feature scaling, there's a problem with standard scalar in the X train and Y train, where it was returning the wrong mean and standard deviation values from the set. And then also towards the end, I calculated the accuracy there using that formula right here, this formula, when the sklearning kit already had an accuracy feature. So overall, I had a really great time working on this project. And although it was kind of difficult, it was rewarding to see the knowledge that I learned this semester applied to a situation that was close to home with my mom. So with that, I'm going to wrap it up, and I appreciate you for listening.